Hello friends, welcome back to my YouTube channel. This is 20th part of my discussion on adsorption, which will be a continuation of the discussion on stage-wise adsorption. And I will be discussing the application of a Freundlich adsorption isotherm to a two-stage countercurrent adsorption. So we will be understanding, or we will learn how to apply the Freundlich adsorption isotherm to a typical two-stage countercurrent adsorption operation. That is, we will know how to deal with a two-stage countercurrent adsorption operation if the equilibrium is described by the Freundlich adsorption isotherm. So in this case, why I am considering two-stage countercurrent adsorption? Because due to the cost of physical separation involved after each stage, it is not economical to have more than two stages in a typical countercurrent adsorption operation. So that's why I am considering a two-stage countercurrent adsorption, where I will discuss how you can apply the Freundlich adsorption isotherm to this operation. So let us start the discussion. So if we have to talk about multistage countercurrent adsorption operation, so what can we say? This operation, multistage countercurrent adsorption, it is carried out in a multistage countercurrent cascade. So it is a countercurrent cascade that is containing multiple stages, and the operation is carried out in a continuous manner. That is, the two phases, solid and liquid phases, they flow from one stage to the other in a continuous manner. And since the operation is countercurrent operation, the two phases will be flowing countercurrent to each other. Now in the discussion, we are going to consider a feed solution as usual. We are going to consider a feed solution, which is a binary solution of two components, binary solution of A and B. A is the solute that is to be adsorbed, and we are going to assume that only A is strongly adsorbed. That means the other component, that is adsorption of B, we are going to neglect. So in this case, B is the unadsorbed substance. The adsorbent phase, first requirement is it should not be soluble in the feed solution. And now you could use a fresh adsorbent in the operation. And if you are doing so, it will not contain any solute on its surface. But the other option is you can use a recovered adsorbent that has been used in a previous operation. And if you are using a recovered adsorbent, then it will contain some solute on its surface. And in my discussion, I am going to consider the last scenario, where the adsorbent that is being used is a recovered one, and that's why it will be containing some solute on its surface. Now, as the number of stages is increased, now here we are going to understand why it is not economical to use more than two stages in a typical multi-stage countercurrent operation. So if you try to increase the number of stages in the cascade, the quantity of adsorbent required, it will decrease rapidly. It will decrease rapidly initially, but it approaches the minimum value only asymptotically. That is, so if you have to understand this with the help of this graph, let us say that you have the quantity of adsorbent on which is plotted on the y-axis, and let us say number of stages you are plotting on the x-axis. So as you increase the number of stages, the quantity of adsorbent required, it will decrease. It will decrease rapidly initially, and then afterwards it will approach the minimum value asymptotically in this manner. So that is the case when you increase number of stages in the operation, in the multi-stage countercurrent adsorption operation. So, but in actual practical applications, since you need an intermediate separation of solid and liquid phases between the two stages, and therefore the cost of separation will increase beyond two stages in the countercurrent cascade. Why the cost increases? Because the cost of intermediate separation of solid and liquid phases between the stages, it will increase beyond two stages, and therefore it is rarely economical to use more than two stages in the cascade. Now let us talk about the two-stage countercurrent adsorption. In this operation, you have the feed solution. It is admitted into the first stage, whereas that the adsorbent phase, it is admitted into the second stage. And the solid and liquid phases then flow countercurrent to each other in the operation through the cascade. So you can represent it schematically. So you have stage number 1, you have stage number 2, and feed is admitted into the first stage. I will shortly tell you these notations. I have discussed these notations in my earlier video lectures. I am giving link to the entire playlist of my video lectures on adsorption in the description section. So I will briefly talk about these notations shortly. So the feed is admitted in stage number 1, and it will be identified by these parameters. Then it will move through the cascade, and finally it will come out of the liquid solution. It will move from stage 1 to stage 2, and finally it will come out of stage number 2. The adsorbent phase, when the liquid phase, it comes out of stage number 2, it will be identified by these parameters. I will shortly tell you what are these notations. Then the adsorbent phase, it is admitted into the second stage. It will be identified by these parameters, and then it will move through the cascade, and finally it will come out of stage number 1, and then it will be identified by these parameters. Then the intermediate compositions or intermediate phases, and that is liquid phase that is coming from stage 1 and then going to stage number 2, it will be identified by these parameters, and adsorbent phase that is coming out of stage number 2 and going to stage number 1, it will be identified by these parameters. Let us move ahead. Now let us talk about the notations. So in this case, L0, L1 and L2. L0, L1 and L2. What are these? These are total mass flow rates of a liquid solution. Total mass flow rate. That is mass flow rates of A and B. A plus B. Then S0, S2 and S1, these are total mass flow rates of the adsorbent phase. That is, it is mass flow rate of solid adsorbent plus the solute. Then LS in this case is mass flow rate of the unadsorbed component, which in this case is B, that is present in the liquid solution. Then you have SS. SS is the mass flow rate of the solid adsorbent in the adsorbent phase. So out of solid adsorbent and E, SS represents the mass flow rate of solid adsorbent. Then Y0, small y0, small y1 and small y2. These are rate fractions of the solute in the liquid solution. So y0, y1 and y2. Small y0, small y1 and small y2. These are weight fractions of solute A in the liquid solution. Whereas capital Y0, capital Y1 and capital Y2, these are weight fraction of solute A on A free basis in the liquid solution. So I have discussed this in my earlier videos. You please, if you have not yet seen those videos, you please watch those videos. Let me just tell you, in this case, capital Y is related to small y by this equation. Capital Y is, just a minute, capital Y is small y upon 1 minus small y. I have discussed this relation. How we get this relation, I have discussed in my earlier videos. Then you have small x0, small x1 and small x2. These are weight fractions of solute E in the adsorbent phase. Whereas capital X0, capital X1 and capital X2, these are weight fractions of solute E in the adsorbent phase on A free basis. Weight fraction of solute E on A free basis in the adsorbent phase. So here also you have a similar relationship between capital X and small x. Capital X is small x divided by 1 minus small x. Let us move ahead. So these are the notations that I have used in the discussion. I hope you have understood what are the notations, how they are defined. If you have any doubts, you please mention them in the comment section. Now we are going to take solute material balance, and for that I am considering the entire cascade. So if you write material balance for solute E, and that too at steady state, which suggests that input mass of A is equal to output mass of A. So the material balance equation will be, now I am directly taking the equation in terms of capital Y and capital X. How you get this equation, you please watch my video lecture on multistage theoretical aspects of multistage counter current adsorption. That is video number 18. In video number 18, you'll understand how I have got this equation. So in this particular discussion, I am directly taking the equation. So if you write material balance for solute E and express it in terms of capital X and capital Y, the equation will be Ls into Y, capital Y0 plus Ss into capital X0. That is equal to Ls into capital Y2 plus Ss into capital X1. So that is Ls into Y0 minus Ls into capital Y0 minus Ls into capital Y2. I have collected the terms containing Ls on the left hand side, and then on the right hand side we have terms containing Ss. So this will be equal to Ss into capital X1 minus Ss into capital X0. So if you take Ls common, it will be Ls into capital Y0 minus capital Y2. That is equal to Ss into capital X1 minus capital X0. And then we can write this equation: capital Y0 minus capital Y2 divided by capital X1 minus capital X0. That is equal to Ss upon Ls. And I am calling this as equation number 1. Now what can you say about equation number 1? Equation number 1, it will represent a straight line on the XY plot, which is the equilibrium diagram. And the line, the line that is represented by equation 1, it passes through these points, capital X1 Y0 and capital X0 Y2. And this line, it has a slope of Ss upon Ls. I have discussed it. You please watch part number 18. So this line has a slope of Ss upon Ls, and then this line is nothing but the operating line for the two-stage counter current adsorption operation. Okay, so once you have got the equation for the operating line, you can plot it on the equilibrium diagram. So here you are plotting capital X on the x-axis, capital Y on the y-axis, and when you plot the equilibrium values, you will be getting a curve, and that curve is the equilibrium curve. Now let us follow this operation on this equilibrium diagram. That is, let us plot the operating line. Now for the liquid solution, you can see it enters into the first stage. So Y0, the concentration of the entering liquid solution, it is capital Y0, and then it comes out of stage number 2 and it has a concentration of capital Y2 in it. That means for the liquid solution, the concentration decreases from capital Y0 to capital Y2. And for the adsorbent phase, as it enters stage number 2, concentration of solute in it is capital X0. And as it moves through the operation and then comes out of stage number 1, concentration on its surface is capital X1. That is, as the adsorbent phase moves through the operation, concentration of solute on its surface increases. It increases from X0 to X1. Now I hope this is clear to you. And then you can see for the liquid phase that is coming out of stage number 1, the concentration is capital Y1. I'm just talking about capital X and capital Y. And then for the stage number 2, the adsorbent phase that comes out of stage number 2, concentration of solute on its surface is, on the surface of the adsorbent, is capital X2. So that means for stage number 1, the leaving streams are, you have the leaving stream is the liquid stream that leaves first stage. You have the liquid that is coming out of stage number 1, the liquid phase that is coming out of stage number 1, and then the solid phase that is coming, adsorbent phase that is coming out of stage number 1. And since they are leaving the stage and we are considering it to be a theoretical stage, X1 will be in equilibrium with Y1. Same is the case for stage 2. The leaving liquid solution, which has concentration of capital Y2, and the leaving adsorbent phase, which has a concentration of capital X2. Since the leaving phases, they are in equilibrium with each other, X2 will be in equilibrium with Y2. This you need to understand. Now we are going to understand this on the equilibrium diagram. So let us understand. So in this case, as I said, concentration in the liquid solution, it decreases from Y0 to Y2. Now you must have understood from the diagram just now. And concentration on the adsorbent phase, it increases from X0 to X1. And then I get these 2 points. This is the coordinates of these points are capital Y0, X1, and coordinates of these points are capital Y2 and X0. And these are the end points of the operating line. This is the operating line. And then you can draw the stages. You can start at the lower end of the operating line and if you start constructing the stages, it will be this first stage will be constructed in this way. You start at this point, Y2, X0, go to the equilibrium curve, and then move vertically to the operating line, then move horizontally to the equilibrium curve, and finally move vertically to the operating line. So in this way, 2 stages get accommodated under the operating curve. Now, this concentration, that is for stage number 1, this concentration will be this point will represent capital Y1, and you can see capital X1 is in equilibrium with capital Y1. And then you can see X2 is in equilibrium with Y2. So X2 and Y2, these are concentrations in the leaving phases. That is, Y2 is concentration in the liquid phase that leaves stage number 1, stage number 2, and X2 is the concentration in the adsorbent phase that leaves stage 2. Y1 is the concentration in the liquid phase that is leaving stage 1, and X1 is the concentration in the adsorbent phase that is leaving stage number 1. So let me just show you so that you understand it perfectly. So I'll just show a simple diagram to tell you. So this is stage 1, this is stage 2. So the feed solution, it is entering stage 1, and I'm just showing the concentrations. So you have Y1, then liquid solution that comes out of stage 1, concentration is, concentration is Y1, and the concentration in the liquid solution that comes out of stage 2, the concentration is Y2. In the feed, the concentration is Y0. For the adsorbent phase, which enters in stage number 2, concentration is X0, and then this solid phase or adsorbent phase that leaves stage 2, concentration is X2, and the adsorbent phase that leaves stage 1, the concentration is X1. So the point is, X1 and Y1, they are in equilibrium with each other, and you can easily understand it over here. Y1, it is in equilibrium with X1, and for the second stage, Y2 is in equilibrium with X2. So these are the leaving phases from stage number 2, and you can easily understand over here, capital Y2 is in equilibrium with capital X2. So I hope it is clear to you how we have drawn the operating line and how various concentrations they are shown on the equilibrium diagram. If you have any doubt, you please mention them in the comment section. So let us call this point as point P and this point as point Q, and let us denote this point as point R. Now, equation of the operating line, we know we can write in two different ways. So if you consider point P and point Q, that is the endpoints. Point P, it has coordinates of x1, y0, and point Q, it has coordinates of x0, y2. So considering the entire operation, that is when you consider points P and Q, you are considering the entire operation. So for that, the equation of the operating line will be written like this: capital Y0 minus capital Y2 upon capital X1 minus capital X0, that is equal to SS upon LS. You can also write the equation considering points Q and points Q and R. So Q, it has coordinates of X0, Y2, and R, it has coordinates of X2, Y1. So in that case, the equation will be written in this way. So when you consider points Q and R, actually you are considering the first equilibrium stage. So the equation will be written as capital Y1 minus capital Y2 divided by capital X2 minus capital X0, that is equal to SS upon LS. So this equation and this equation both represent the same operating line. That is, you can write the equation of the operating line with two different sets of points. So I hope you have understood it. If you have any doubt, you please mention them in the comment section. Now for dilute liquid solutions, we know the equilibrium is described by the Freundlich adsorption isotherm. So when you are dealing with dilute liquid solutions, the Freundlich adsorption isotherm, it will be described by the Freundlich adsorption isotherm, it will describe the equilibrium. So the equilibrium curve, it is represented by equation of the following form. So if it is Freundlich adsorption isotherm, the equilibrium curve will be represented by an equation of this form: capital Y is equal to m into capital X raised to n, where m and n, these are constants. So idea is, whenever you are solving any numerical that is based on a Freundlich adsorption isotherm, you have to get the values of the constants, and you can obtain them by plotting the data that is given to you. Now, equation of the operating line, if you consider the entire operation, we just saw it. So the equation is capital Y0 minus capital Y2 upon capital X1 minus capital X0, that is equal to SS upon LS. And if you are using pure adsorbent, in that case capital X0 will be equal to 0. X0 is 0. And if you use this in equation, it will be capital Y0 minus capital Y2 divided by capital X1, that is equal to SS upon ELS. And since X1 is in equilibrium with Y1, we have just understood it. They will be related by the equilibrium equation. So you can write this equation, capital Y1 is equal to M into X1 raised to N. That is Y1 upon M is equal to X1 raised to N. That is X1 is equal to Y1 upon M raised to 1 upon N. And now you can use it in equation number 3. So it will be Y0 minus Y2 upon Y1 upon M raised to 1 by N, that is equal to SS upon LS. And I will call it as equation number 4. Then if you consider the other equation for the operating line, when you consider the first stage, the equation is capital Y1 minus capital Y2 upon capital X2 minus capital X0, that is equal to SS upon LS. If you are using pure adsorbent, then X0 will be 0, and in that case the equation will be capital Y1 minus capital Y2 upon X2, that is equal to SS upon LS. I am calling it as equation number 5. Now since X2 is in equilibrium with Y2, they will be related with each other by this equation. So you have capital Y2 is equal to M into capital X2 raised to N, that is Y2 upon M is equal to X2 raised to N. That is X2 is equal to Y2 upon M raised to 1 by N. Now if you use it in equation number 5, you will get this capital Y1 minus capital Y2 divided by capital Y2 by M raised to 1 by N, that is equal to SS upon LS, and I am calling it as equation number 6. So we got these equations. You have Y0 minus Y2 upon Y1 upon M raised to 1 by N, that is equal to SS upon LS. That was equation number 4. And then we got this equation as well. Capital Y1 minus capital Y2 is equal to capital Y2 by M raised to 1 by N, that is equal to SS upon LS. That was equation number 6. Now the right hand side of equations 4 and 5, they represent the same quantity, that is SS upon LS. So you can equate the left hand sides of those two equations. So from equation 4 and 5, you have, by equating the left hand sides, capital Y0 minus capital Y2 divided by capital Y1 by M raised to 1 by N, that is equal to capital Y1 minus capital Y2 divided by capital Y2 divided by M raised to 1 by N. So we will simplify it. That is Y0 minus Y2 upon Y1 minus Y2 is equal to, I have rearranged it, capital Y1 by M raised to 1 by N divided by capital Y2 by M raised to 1 by N. Then I can write in this way in the next step, capital Y0 minus capital Y2 divided by capital Y1 minus capital Y2. And since you have the same power for the two terms, you can write it in this way, capital Y1 by M into M by capital Y2 raised to 1 by N. So M will get cancelled, and you are left with capital Y0 minus capital Y2 divided by capital Y1 minus capital Y2 is equal to capital Y1 by capital Y2 raised to 1 by N. That is, again, I will make some rearrangement. So I'll divide with capital Y2. So it will be capital Y0 minus capital Y2 upon capital Y2 divided by capital Y1 minus capital Y2 divided by capital Y2, that is equal to capital Y1 by capital Y2 raised to 1 by N. So that is Y0 upon capital Y0 by capital Y2 minus 1. So when I separate the denominator, same thing in over here. So capital Y1 by capital Y2 minus 1, that is equal to capital Y1 by capital Y2 raised to 1 by N. So that is capital Y0 by capital Y2 minus 1 is equal to, I'll bring this to this side. So it will be capital Y1 by capital Y2 raised to 1 by N into capital Y1 by capital Y2 minus 1. And this is the equation. So in this equation, provided that Y1, Y0, the initial concentration in the liquid solution and the final concentration in the liquid solution. So if they are known to you, you can solve this equation. You can solve this equation to get Y1. And once Y1 is obtained, let me just tell. Once you get Y1, if you solve after solving this equation, then by using the equilibrium relationship, Y1 is equal to m into x1, you can get the value of x1. That is, you'll be able to get the compositions in the two phases that are leaving stage number 1. And this can be used to plot the stages, or you can use it in the equation of the operating line and get the quantity of adsorbent that is required. So in my next video lecture, I'll be using this equation to get the quantity of adsorbent that is required in a typical two-stage countercurrent adsorption operation. So I hope the steps are clear to you. Very simple steps. The objective was to get this equation. This equation is useful for finding Y1 if Y0 and Y2 they are known to us, and once Y1 is known to us from the equilibrium relationship, you can get capital X1. Let us move ahead. So we got the equation capital Y0 by capital Y2 minus 1, that is equal to capital Y1 by capital Y2 raised to 1 by n into capital Y1 by capital Y2 minus 1. So I have just talked about how to use it. This equation, it can be solved for Y1 when capital Y0 and capital Y2 are known, and when Y1 is known to you, X1 can be obtained from the equilibrium relation, which is the Freundlich adsorption isotherm. That is, capital Y1 is equal to m into capital X1 raised to n. So finally, the quantity of the adsorbent can be obtained from the slope of the operating line. So this is the slope of the operating line, capital Y0 minus capital Y2 divided by capital X1 minus capital X0, that is equal to SS upon LS. So here we have considered the entire operation, and then you can get SS from this equation. So as I said, in my next video lecture, I'll tell you how to solve a numerical and get the quantity of adsorbent by this approach. So I hope the concept is clear to you. If you have any doubts, you please mention them in the comment section. Now let us talk about minimum adsorbent to solvent ratio, that is SS minimum by LS. I have discussed it in my lecture number 18, part number 18. So the solvent in this case is the unadsorbed component. So that's why in the ratio, the solvent that we are talking about is nothing but the unadsorbed component, that is component B. SS minimum by LS, it corresponds to the largest slope of a operating line that touches the equilibrium curve. So out of all those operating lines that touches the equilibrium curve within the specified concentration range, SS minimum by LS represents the largest slope, the operating line with the largest slope. So SS minimum by LS, it corresponds to the largest slope of a operating line that touches the equilibrium curve within the specified concentration range. I have discussed this in my video number 18. You please, the link to the entire playlist I have given in the description section. Now the point at which the above operating line touches the equilibrium curve, this point is called the pinch point. And the location of the pinch point, it will depend on the nature of the equilibrium curve. So accordingly, when the equilibrium curve is a straight line or it is concave upward, the pinch point will occur at the concentrated end of the cascade, that is left side of the cascade. So if the equilibrium curve is a straight line or it is concave upward, then the pinch point is going to occur at the concentrated end of the cascade. I will show that shortly. The concentrated end of the cascade, it occurs at the left side. and when the equilibrium curve is concave downwards, the pinch may occur at the point of tangency. So, by the use of Freundlich adsorption isotherm, you can find the minimum adsorbent to solvent ratio only for the first case. That is when the operating line, the equilibrium curve is a straight line or it is concave upward. For the other case, that is when the equilibrium curve is concave downward, you cannot use, you have to locate the point, pinch point, graphically. So next I'll be discussing how to get the pinch point for the first case, that is when the equilibrium curve is a straight line or it is concave upward. So minimum adsorbent to solvent ratio, that is SS minimum by LS. So I can show. Now I have considered the case where the equilibrium curve is a straight line, and in that case the pinch point, it will occur at the concentrated end. So here at the pinch point, as you see it over here, it will have coordinates of y0 and x1. And this x1, when this happens, when the operating line touches the equilibrium curve, the concentration that is obtained is maximum. That is, x1 will be maximum, and I am denoting it as x1 max. So at the pinch point, the equilibrium curve and the operating line, they intersect each other. Therefore, x1 max and y0, this point, lie both on the equilibrium curve and the operating line. That is, this pinch point, it lies on the operating line. At the same time, it lies on the equilibrium curve. So therefore, this point x1 max y0, it should satisfy the equation of the equilibrium curve. So in that case, that is, it should satisfy the equations of equilibrium curve as well as the operating line. Then for the case where the equilibrium curve is concave upward like this, then again the pinch point is going to occur at the concentrated end over here. So you get this point. The coordinates of this point are y0 and x1 max. x1 in this case will have the maximum possible value. I am denoting it as x1 max. So as the pinch point, at the pinch point, the equilibrium curve and the operating line, they intersect with each other. I have talked about it. Therefore, the pinch point with this concentrations x1 max, capital Y0, it lies both on the equilibrium curve and the operating line. Therefore, x1 max and y0, the point with coordinates x1 max, capital Y0, that is this pinch point, it should satisfy the equations of equilibrium curve and the operating line. And then you can get the value of x1 max, and then I'll tell you how to use this information. Right now, you must have understood how the pinch point occurs at the concentrated end of the cascade, if the equilibrium curve is a straight line or it is concave upward. Okay, so in this case, the pinch point, which has coordinates of x1 max, y0, it satisfies equations of the equilibrium curve and the operating line. We have understood it. So if you use the equation of the equilibrium curve, you have this equation, capital Y0 is equal to m into x1 max raised to n. That is, capital Y0 by m is equal to x1 max raised to n. That is, x1 max is equal to y0 by m raised to 1 by n. And if you use it in the equation of the operating line, so it will be capital Y0 minus capital Y2 divided by capital X1 max minus capital X0. And since you are using X1 max, SS will be SS minimum. So this is equal to SS minimum by LS. So everything on the left side will be known to you. You can use those known values and get the minimum adsorbent to solvent ratio. So in this way, we can use the Freundlich adsorption isotherm to get the minimum adsorbent to solvent ratio. It is difficult to use if the equilibrium curve is concave downward, because in that case, the pinch point occurs at the point of tangency. So with this, I will end my discussion for this video lecture. Here I have told you how to use the Freundlich adsorption isotherm to get the amount of adsorbent that is required in the operation, and then how to use it to get the minimum adsorbent to solvent ratio in a typical two-stage countercurrent adsorption operation. So with this, I will end my discussion for this video lecture. In my next video lecture, I will be discussing a numerical which will have the application of today's discussion, which will have the application of Freundlich adsorption isotherm. So I hope you will join me in my next video lecture. Thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. In my next video lecture, I will be discussing a numerical example that is based on the discussion in this video lecture. Thank you. Have a nice day and hope to see you soon in my next video lecture.